Yeah, please. I mean, also, I prepared like way too much, but in part just because I don't know what exactly you know and don't know and want to know. So if you want me to go off on certain tangents, tell me. So the basic background, so toric origami manifolds and origami templates. First, I should tell you at least a few words about toric manifolds. And so the framework that I am coming from is in symplectic geometry. And so the key gadgets there are toric symplectic manifolds. And I don't know how much geometry you guys want to know, but I'm inclined just to sort of do as much combinatorics and as little geometry as possible. Is that the right way to default? Okay. Okay, and anywhere you want me to go back to geometry, tell me. But so the key thing here is, so toric, well, okay, so manifold, we have some manifold. It's symplectic, so it's always even dimensional. We'll call it 2n dimensional. I guess it doesn't really matter. Actually, I'm going to use D because there's D's 2D dimensional, and toric means that there's a TD acting on it. And we're in the symplectic framework, so I'm just, a TD is an S1, yeah, it's just a compact torus. And the action, so we're in the symplectic framework. This should preserve the symplectic geometry. It should be what's called a Hamiltonian action. And that means that we have a map to RD. And one of the first theorems, and there are a couple theorems. Yeah. Oh, sure. Yeah, I was suppressing that just because, but if you want to hear it, I'm happy to. Yeah. I'm assuming you don't know them, but I'm happy.
You should give one example.
Yeah, okay. So let's have examples. I'm going to try to. What I should. Well, okay, I won't say that just yet. So the first example is just S1 acting on S2. That is Hamiltonian, and one of these. So Hamiltonian means preserves the symplectic geometry. It preserves the symplectic form. Okay, good. So let me. Okay, so let's see. So. Okay, so if M is a manifold, a symplectic form is a 2 form. Okay, that means that at any tangent space, it eats 2 tangent vectors and spits out a number. And it should be closed and non-degenerate. Non-degenerate means at any point, if I have a non-zero tangent vector, there must be some other non-zero tangent vector so that the symplectic form spits out a non-zero number. Okay, so there's always a symplectic buddy that pairs non-zeroly. So on S2, and in fact, let's not even think about actions yet. Let's just think about manifolds. On S2, or on any orientable surface, omega of 2 tangent vectors at a point P, this is just going to be the signed area, the determinant of the 2 tangent vectors. So the signed area of that parallelogram.
What is the map? It's from R to R?
Sorry, oh, this map?
No,
This. So what it is, at any point, it takes two tangent vectors
so what's the intended map?
and spits out a real number. And it's anti-symmetric, so omega p TPM is one vector, so these are tangent vectors. Exactly. Well, that's the first question, actually. So the tangent space is some linear vector space. Okay, so I have a manifold. The tangent space is a linear space. And actually,
Some subset of Rn?
yeah, it's some subspace of, if I think of my manifold as embedded, or if I have sort of local coordinates, it's some subspace Rn. Okay, and this is a bilinear form. It's skew symmetric. And it's non-degenerate. And non-degenerate means that for any non-zero vector, I always have a buddy so that I pair non-zerally. And what that means, what that's actually going to tell us about this vector space. So I choose a non-zero vector. I'm thinking about choosing a basis. Okay, so I start with a non-zero vector. I have a buddy that pairs non-zerally. I split off those two dimensions, and I keep going. Choose another non-zero vector for the basis. Choose a buddy. Keep going. And so what you get from this non-degeneracy is your basis always has an even number of elements. So the manifold is even dimensional. So d omega, this is the derivative. The derivative has to be 0. This is the derivative in the sense of differential forms. So it's some notion of derivative. This is some sort of global condition. And so this says something interesting. I'll tell you in a second. But what this says, the other thing that this says, it first says that M is even dimensional. The other thing it says is if I take a top power, so let's say M is 2-dimensional, 2D dimensional. So then omega to the D goes from sort of the top power of TPM to R. Really, because it's anti-symmetric, it goes from the exterior algebra, the top exterior algebra. And it's the non-degeneracy says that this is sort of a non-zero form everywhere. So it says that M has a volume form. Okay, so M is an orientable manifold. Okay, so in the framework of two-dimensional manifolds, which are the easiest ones to understand, or the only ones I can draw, in the framework of two-dimensional manifolds, well, on a surface, an orientable surface, we have this form that just takes the determinant of the two vectors, and so that gives signed area because we know determinant is anti-symmetric. Then the non-orientable ones do not have one. Okay, so the Klein bottle is not a symplectic manifold. Another thing that this closed business tells us closed says, oh, sorry.
The top volume in the case of it was sphere S.
Oh.
Then it would be also determinant of the flow vector.
That's right. That's right. Except, yeah, that's right. So we want to. So that's the the good next question, is S4 an example? And what I was just going to say was that, okay, the fact that this is closed, let's see, so omega is closed, and so powers of it are also closed. So, oh shoot, how does this go? Let's see, so, okay, so this is closed, and so it potentially represents something in homology or cohomology, depending. Okay, and so Stokes' theorem is going to allow us to show that it must be something non-zero. So it's closed. It's going to be 0 if it were exact. How do I get this? Oh, I didn't do this, and I'm going to get it wrong. Let's see. Here's what I want to do, right. So, okay, Stokes' theorem says that if I integrate a form on the boundary, that's the same as integrating d of the form on the whole manifold. And so then this is going to be omega to the d. This is the volume of the manifold. And on the other hand, if this were exact, I would be able to express it this way. And this would have to be 0 because the sphere has I'm looking at a closed compact manifold with no boundary. And so that wouldn't work. So this must be false. And so in particular, H2 can't be 0. S4 only has homology or cohomology in degree 0 and 4, so this one can't be symplectic. Okay, so the four-dimensional ones, the simplest four-dimensional one, so we know that it had better have H2 and it had better have H0 and H4. And so the simplest thing that has all of those and nothing else is CP2. Okay, that is the moduli space. That's a fancy word, but it's just the set of all I look at all complex one-dimensional subspaces of C2. Okay, and this, oh yeah, S2 times S2 is simpler. Okay, that was simpler, sorry. Sorry. And then here the form is the product, yeah, exactly.
Okay, so maybe we deviate, yeah.
Mm-hmm. No, that's fine. I wanted to put up all these examples anyway. So, okay, so we have all of these examples. Okay, so this is what a symplectic manifold is. I'm going to be interested in the ones where there's an action preserving the symplectic form and satisfying some differential equation. And I'm happy to go through this, but I first want to tell you what the consequences are, and then you can tell me whether you want to hear the details or not. Okay, so the consequences are this. These conditions don't require D and 2D to be the same. These conditions imply that if we have TK acting on M2D, then K is less than or equal to D. Oh, I should say effective. Okay, and so what Atiyah, Gilliman, and Sternberg showed in 1981, faithful, yeah. What they showed is that, so this differential equation gives you this map from, well, it will be from M2D to RK. The D is the dimension of the torus. Okay, they showed that phi of M, if M is compact, which all of our examples are.
What would be phi in the case of
Okay, yeah, good. So first we should ask whether there are any examples here. Let's see, so okay, so first we have the circle spinning that guy around. That one is Hamiltonian, and the function is the height function. On T2.
It's the only invariant of this.
That's right. Okay, for T2, we can spin, I mean, T2 is T2, so we can sort of spin that way or that way. It turns out these both preserve the symplectic form, but they don't satisfy this differential equation. It's just take the signed area, just the flat, yeah. And of course, this doesn't have a circle action because we have sort of, if you have at least two holes, there's no way to have a rotation. Now, of course, this wasn't symplectic, but we do have a circle symmetry going around, and that will come up later. Here we have plenty of symmetries. I mean, if we think of S4 sitting in, let's see, normally we think of it as sitting in R5. If we add one more dimension and think of it as sort of sitting in the plane in R6. Well, am I getting this right? Oh, ignore the height, yeah. Okay, so I'm going to think of this as C. So this I'm going to think of as a Z1, a Z2, and a T. And I still have norm Z1 squared plus norm Z2 squared plus T squared equals 1. And we can ignore the fact for a moment that it's not symplectic. Oh, and now I should have written this bigger. And then we can just act on this by, let's see, T1, T2. We just rotate the two complex coordinates, and that defines a two torus action is perfectly nice, but we weren't in the framework already of symplectic, so we don't have this map. On here, we can act by a circle and a circle independently. Yeah, it's just a product action. And so so here we can, so it seems like a silly thing to do, but we can actually scale the symplectic form. So remember, symplectic form was just telling you area. And so it's sort of telling you how big your sphere is. So I could think of this as a little tiny sphere, product a really big sphere. And then my momentum map lands in R2. And this will go to sort of a rectangle rather than a square. Okay, but we could scale it to whatever rectangular square that we want. CP2, let's see. Oh, shoot. I got something wrong. This should have been in C3. So C3 has a T3 acting by rotations like this. And if I apply a rotation to C3, I can apply a rotation to a subspace, and I get some other subspace. So T3 acts on all of this. However, the diagonal TTT is going to send every line to itself just sort of bigger, but it's not going to change the line. And so this has an effective, a faithful T2 action, which I can think of as T3 modulo the diagonal circle. And that has momentum polytope, momentum image, a triangle.
The image of the map. Phi is the momentum.
That's right, phi is the momentum map. And this theorem says that phi of m is always a convex polytope. And more than that, it's the convex hull of the images of the fixed points. It's unique up to a constant. It's defined by a differential equation, and so you can always sort of adjust your function by adding a constant. Which one? The CP2? Yeah. So the action, maybe it's better if I write out CP2 in coordinates. Okay, so in CP2, we can think about homogeneous coordinates. So I just think of a Z0, Z1, and Z2 defining a plane inside of C3, and lambda Z0, lambda Z1, lambda Z2. If I multiply them all by the same complex number, they define the same plane. So these are my coordinates. And then I'm going to do, so the T3 action on CP2 coming from CP3 just says that T1, T2, T3 oops. Oh, sorry. That's awful, but that is what it is. Okay, so I just rotate each coordinate, and so then I change my plane. And in this way, so also we can see that TTT is going to fix it because it's going to send Z1, Z0, Z1, Z2 to TZ1, okay, TTT. So it's really only a T2 action. So I can just sort of forget about this one, say, and what the momentum map is if I write it in those coordinates. Is going to send Z0, Z1, Z2 to and it better be a homogeneous function in order to be well defined. And what it's going to send it to is Z1 squared divided by the sum of all of them squared, Z2 squared divided by the sum of all of them squared. And the image of that is the convex hull of 0, 0, 1, 0, 1, 1.
So the extreme points are just the two zeros?
Exactly. The extreme points and the points that are fixed. If I have 1, 0, 0, that's not going to move under this action. Or 0, 1, 0, that's not going to move under this action. And so those are the fixed points, and that's exactly this again.
Can you maybe write the differential equation? Otherwise, I don't know.
Sure. Oh, and then I should have written the symplectic format. Oh my goodness, okay. Okay, it's not, I can say it's a differential equation, but it's,
So the last thing in this theorem is that all of the complex part, right? The limit has to lie inside the complex part.
well, actually, you prove this, the proof is by induction, the proof that I know better. So they have different, Atiyah and Gillen and Sternberg had different proofs. Atiyah's proof is by induction on the dimension of the torus. And in one dimension, you can see this fixed point business pretty easily, because in one dimension, oh, I have to write down the differential equation. Okay. But in one dimension, what you can see, you have this function, and you can see that the critical set is sort of naturally the fixed points, and well, the extremal points have to be critical. So it's not saying very much in one dimension. But then you have this bootstrapping technique where this is related to the fact that the level sets of this map are also connected. And so there's this bootstrap back and forth between the level sets being connected and then bootstrapping it up to the next dimension.
In the other proof, you show that locally around any point, the symplectic point has to look like a certain thing, and the Neumann map has to look like a certain thing, and the image is always, if it's not fixed at all, then it
sort of has a, looks, I see.
And if it's fixed by a one-dimensional thing, then it looks like just a half plane, and if it's fixed by
It sort of looks like a corner. I see.
So you show that everywhere it sort of looks like a polytope,
And then it
sort of
globally
there's
has to.
local global
I see.
thing. But it all also must be.
Yeah, that's right. I mean, both proofs rely on the fact that the components of that are all Morse functions, and so you have a lot of Morse functions on your manifold, nice ones. So we have plenty of time. Yeah. So do you want to see the differential equation? I mean, do you want to see it? It's enlightening in a certain way. Okay. So let's see. So we have this 2 form. And we. Okay, so we have this. Yeah, I'll write it. And okay, so we have this 2 form. The fact that it's symplectic that means, okay, I need some notation. So for each. So this T action, for each G in T, I have a diffeomorphism, tau G from M to M. And preserving the symplectic form is the same as saying that the pullback of the form is the form for every G in the group. Okay, and so that we can see both here and here. If we sort of measure area and then rotate it around, we're measuring area, that's the same thing. And so these both preserve the symplectic form. Another way to write this is in terms of the vector fields that the action induces. So a vector field on a manifold is just a tangent vector at every point. And for any vector in the tangent space. Oh my gosh, this is where this is going to look horrible. Okay, so I look at the tangent space to the torus. sorry about the notation. Maybe I should make this torus like that so the tangent space doesn't look the same. This is just the Lie algebra. For every x in here, I can sort of exponentiate that down into the group, look at how that one parameter subgroup is acting, take a derivative, and I get tangent vectors to my manifold. Okay, so in equations, oh, shoot. I'm going to call that xc. Then xc at a point P, this is supposed to be a tangent vector at P, so I exponentiate xc for all real numbers. So I get a one parameter subgroup. I look at how that acts on P, and then I take a derivative. Okay, that gives me a tangent vector at P. And this, it turns out, is equivalent to the Lie derivative of the form along the vector field should be 0. So saying that something is preserved is the same as saying the derivative is 0 when you're looking at the change along the action. Okay, but the Lie derivative has a, by Cartan's magic formula, is d of IXC omega plus IXC d omega, where this IXC just says stick XC into the first slot of omega. Okay, here d omega, this is where we use the fact that d omega was closed, so that's 0. And okay, so this is just saying that d omega of xc blank, okay, this is now one form, and we're saying that it's closed. Okay, so that's just what symplectic, that's what just preserving symplectic means. So this extra differential equation is that says that omega of xc is exact for every xc. So that means that this is d of a 0 form, which is just a function. Okay, and it's defined only up to its derivative, so that's where the constant comes in. Okay, I should say a little more. Somehow, oh gosh, I do have, well, maybe I shouldn't. Yeah, okay, so that's where the differential equation comes from, and it's easy to work out in sort of simple examples here. For the two-sphere, omega is d theta wedge dh. I'm basically looking at tangent vectors to orbits, sort of scaled by how fast the orbit is going around, inversely scaled. And so my xc in this case is d theta, or sorry, d by d theta. And so when I stick that into the first coordinate, what I get is d of h. So here theta was my angle coordinate and h was my height coordinate, and this is d of height. So that's where height comes from. You sort of, over here you think, okay, well, omega is just dx wedge dy and sort of flat coordinates, thinking of this as r2 mon z2. And then if I'm acting, say, on the x coordinate, I get d by dx, and so omega of xc is just dy. But that y, when I'm looking at r2 mod z2, that y is a circle coordinate, not a r coordinate. And so that's the issue. Okay. Okay, so the second theorem about these actions. Okay, so this is toric when d is equal to half the dimension. Okay, and what Delzant showed is that compact toric symplectic manifolds, say of dimension 2D, are in one-to-one correspondence with a nice class of polytopes. Simple, smooth, rational polytopes in RD. Okay, so simple means that at every vertex of the polytope I have exactly d edges pointing out. So in R3 I have exactly 3 edges. Smooth.
Can you give an example?
Oh, yeah. Like an octahedron. So in R2, the problem is that, of course, everything is smooth, because in R2 we only have polygons. In R3, like an octahedron has that top vertex with 4 edges coming out instead of 3. Okay, so a tetrahedron is good, and an octahedron is bad. Cube is good. And of course, a cube is a product, so that's just S2 times S2 times S2. Let's see, so maybe I was supposed to, I don't remember if smooth, or I don't remember which order these are really supposed to go in. But smooth smooth means that at a particular vertex, if you look at the edges pointing out of that vertex, and rational means that those edges have to point in lattice directions. Okay, so you can't have something with coordinates pi e or whatever. Okay, so and smooth means that the primitive ones have to be a lattice, a z basis of the lattice. Okay, so okay, so with my standard lattice, oh, sorry, it should be z to the d, yeah. I wish I have this really great, when I was in music class in school, the teacher had this thing that made scales, like it was a piece, it had 5 pieces of chalk, but you can get that and just make a scale and then do it that way, and then you have a lattice. It's great. Okay, but so how it sits with respect to the lattice is important, okay, because that diamond, which looks like a square, but it's shifted, if I look at the edges from this vertex, I can't get to that lattice point with z combinations of those edges. Okay, so this is not smooth.
So these from every vertex, you look at the edges going out.
Yeah. And so, yeah, so this is, oh, for every vertex, yeah. Okay.
So d equals 1, you just have 1.
Exactly. And so it's not saying very, and okay, so there are, let's see, so a way to construct the manifold, I mean, so there's sort of 2 directions showing that the polytope has to satisfy these properties, and then given a polytope, producing a symplectic manifold. The way that you produce a symplectic, I mean, I'm not so interested in the symplectic structure because in a moment I'm going to throw that out anyway. But the topologically, you can reconstruct the manifold in the following way. So you can reconstruct M from delta which I can think of living inside of RD with a specified lattice. Okay, so first I look at, okay, I guess first I'll write this down and then I'll show you what's going on in my example. In the S2 example, which is, well, okay, maybe we can do more. Oh, what I should have said before I started saying this was that in this special case, the momentum map so the momentum map always has to take orbits to a point. And so I can think of the momentum map as a map from the orbit space to the convex polytope. And in fact, if I think of it that way, phi from M mod T to this polytope, this is a homeomorphism. So maybe I should call this the orbit moment map. Okay, so I can sort of reconstruct M by sort of taking delta across the whole thing and then collapsing where the orbits weren't quite big enough. So at the vertices, those are supposed to correspond to the fixed points. So I need to collapse the whole torus. And elsewhere, I have to collapse a little bit less. So how you collapse a little bit less is determined exactly by this lattice business. Okay, so okay, so 2 points are equivalent if I'm only ever going to collapse points that have the same coordinate in the polytope. And then if ever this point is in a facet, I'm going to, so each facet is defined by its unit normal vector. The unit normal vector determines a circle in my torus, and I'm going to collapse that circle. And so to collapse that circle, I need TS inverse to be in this circle. Okay, so let's do an example.
Can you tell the number of holes from this description?
The number of what?
The number of holes, let's say, in your manifold.
Oh.
If I give you the convex polytope.
Oh.
Or other topology.
Yeah, so you can completely determine the Betti numbers from the polytope. The Betti numbers are exactly the H vector of the polytope. And in fact, that's how, so Stanley proved this G theorem, or part of the necessity part of this G theorem. And that's exactly how. He said, well, okay, you have a polytope. The H vector is just the Betti numbers of, if it's a smooth polytope, it's just the Betti numbers of this toric variety. It's and that the H vector is symmetric is just Poincare duality for the cohomology ring. And I'll write all this down in a second. And the monotonicity of the H vector is something called Hard-Lefschetz property of Kähler manifolds. I'll write that down in a second. But first, I just want to see how this works. So for S2, well, okay, for any, okay, we already saw that. Oh,
You're going to build a sphere from the interval.
yeah, I'm going to build a sphere from an interval. Okay, I take a circle. I take this cross a circle. Okay, and now the facets are the north pole and the south pole. And the normal just defines the circle inside the circle. So I'm going to collapse the circles. And I got a single point at the north pole, a single point at the bottom, and then everything else remained a circle. Okay, and the size of the length of the interval essentially tells me how big my sphere is. So you can sort of guess that this is maybe telling you something about the symplectic form as well. Okay, so let's see, I want to actually write down some of those topological properties. Oh, maybe I'll write it down over here. Mm-hmm.
Is it obvious that the image is connected?
Yes, because M is connected and that's a smooth map. So the image of a connected set under a smooth map has to be connected. Compact, yeah, sorry, compact. There are sort of more general statements. So this convexity, there are more general statements in in some non-compact cases if you have additional assumptions. This can be generalized to non-compact toric symplectic manifolds, but in that case, it's much more complicated here, and it's also not a one-to-one. There's a uniqueness issue if the image isn't simply connected. Okay, so. Okay, so there's a lot that you can do. So the first thing I said was that let's see. So this delta is going to have an F vector. Just the number of facies of each degree. And then if you put those in a generating function and change t to 1 minus t and multiply it all out, you get what's called the H vector. Oh my gosh, or maybe you also have to call f minus 1 equals fd equals 1. Or, okay, so there's, in any case, you get an h vector, h0 up to hd. And it was noticed that this h vector satisfies some nice, I mean, whoever thought to do that, I don't know. And well, maybe McMullen. Why he thought to do, I mean, it's a random thing to do, right? But I guess combinatorialists are really good at finding interesting phenomena in ways that I could never. Okay, but so this h vector seemed to satisfy hk is equal to hd minus k, and h0 is less than or equal to h1. And I think there's one other property about how quickly the h's can grow. I don't know. Is there? Yeah, there's log concavity. It's something like that. And so these properties were, it was sort of conjectured by McMullen that these properties always had to hold. Stanley showed that they always hold. And Balera and Lee showed that if those properties hold, then there is a polytope that has those combinatorial numbers. Okay, so Stanley. But the way that Stanley showed, that these two properties were satisfied was if you have a polytope, then you have this manifold. M is a toric symplectic, well, for some polytopes. Okay, so this is always going to hold because there's sort of a generalized Poincare duality for intersection homology, and this is definitely there's something very special about the fact that there's a toric symplectic manifold here. So so hi, he showed that hi is the rank of h2i of M with r coefficients. And then the fact that this is a manifold says that hi is HD minus I. This is called Poincare duality. And this increasing up to the middle business is called hard Lefschetz. And it's hard to prove that. What hard Lefschetz says is if you, so we know, or I sort of hand-waved the fact that omega had to be something non-zero in cohomology. And what hard Lefschetz is, it says that if you take the cup product with omega, you go from hk to hk plus 2. And if you do that a bunch of times and you get up to, you get an isomorphism, you have a sort of canonical isomorphism once you fix omega. And in particular, H2 has to inject into H4, H4 has to inject into H6, and so each of these ranks has to be increasing. All the odd ones are 0, it turns out. That's not obvious from anything I've said so far. But let's see. So more is true. I mean, the way that you show that these are the Betti numbers is you show, oh my gosh. Okay. It's actually a little bit easier. Well, okay, so you show that this cohomology ring is the face ring of the polytope. Okay, so what that is, oops. This works over Z. It's generated by n classes, each of degree 2. And there's one of these for each facet of the polytope. And so I think, sorry? And so how you multiply, you just multiply them, and you'll get something 0 when the corresponding selection of facets is empty. Okay, so x, the product over I in I of xi is in the ideal that I'm killing whenever the intersection is empty. Oh, and exactly. So whenever, so basically this is saying I have a cohomology class for every face of the polytope, namely the monomial corresponding to those non-empty intersecting facets. And then there's some pesky linear relations. It's actually easier to work with the ring without the linear relations, and that turns out to have a topological interpretation as well. This is, it turns out, the equivariant cohomology. Okay, so that's just some cohomology that takes into account as well the action. Okay, but what you can deduce from this, so these are all in degree 2, so H odd is 0. In particular, H1 is 0, so pi 1 of m is a perfect group, whatever that means. But it turns out that actually m is simply connected. Yeah. I mean, so there's the abelianization of the fundamental. Oh, okay. The abelianization of the fundamental group is the first homology, and so you have to be careful about torsion versus not. Okay, but in any case, it's simply connected. You can prove that directly. Oh, and I should say who this is. I mean, this. So Stanley uses this presentation to show this, but this presentation is, I think, the earliest place it's written is Danilov, Turkovitz. Actually, I don't think they're both on the same paper, but in any case, it's called that theorem. I'm not sure exactly of the history. So there's also a description of this. So here we're playing with polytopes. Algebraic geometers prefer to play with fans. So that's another combinatorial gadget associated to a toric variety. And what it is, okay, so if this is my polytope, I can take a fan that is, let's see, so a fan is a collection of cones in the same dimensional affine space. And my one-dimensional cones are going to be exactly the rays normal to my facets. And then I take cones whenever there are non-empty intersections. So these cones correspond to the fixed points. And this ring has a nice description combinatorially in terms of the fan. This ring you can describe as piecewise polynomials on the fan. So polynomial functions, a polynomial on each maximal cone, and they have to agree on the intersections. Piecewise polynomials. And this, let's see, so this, recognizing it as this piecewise polynomial, this is due to Bolera and Rose. Oh, right. I was supposed to say a little bit more. So I was able to construct from this polytope the manifold. Operations I do on the polytope can be I mean, if you have a polytope, you can do things like chop off a vertex and replace it with a little simplex. That has a geometric analog. So chopping off a vertex corresponds to doing what's called a blow-up in algebraic geometry. You can also take symplectic cuts. So that's just saying slice your polytope by a hyperplane and take one piece. Or you can do various operations on the polytope, and there's natural reflections in what's happening in the geometry. I think that's everything I wanted to say about the toric stuff. About the I will say, let's see, there are. I don't know when I want to say this. Maybe not yet. Okay.
What do we need to know for the sequel?
I mean, what matters is, like, the important things, let's see. So, where did my green chalk go? These are important. Having this face ring is nice. Well, face ring modulo linear relations, and both this face ring and the piecewise polynomials, those are sort of useful features that allow us to relate sort of topology of M to combinatorics of some gadget. Yeah.
Do you want to take a 5-minute break, or it's up to you?
It's up to you, sure. Yeah, maybe we should. It's always a good idea. But so what I want to talk about, the rest of what I want to talk about is how, like what combinatorial gadgets you get when you get rid of some of the geometry. Okay, so if you...
Everything you said so far is kind of well understood and doesn't present problems to work on, or are there still things to be rounded out?
I mean, well, okay, so I think there are still things one can ask. I mean, the reason toric symplectic toric manifolds are useful, like they're just a really explicit class that you can play with. And so if there's something you want to know, it's the first class of examples you go to. I mean, basically, so for example, there are symplectic invariants you might want to compute. You might want to know which symplectic manifolds embed in which other symplectic manifolds. And there are some obvious ones. S2 embeds into CP2 by, well, CP2 had this triangle, and here's a nice little S2. Okay, but you might want to ask more complicated questions. And already, it's sort of pretty well understood when you can embed balls into 4-dimensional toric manifolds. But that's a very small, it's not very well understood for higher dimensional toric varieties what balls you can embed in a higher dimensional toric manifold. Okay, so there certainly are still things one doesn't know. And sometimes, and they're reflected in some very subtle way in the polytope that it's also not fully understood. So. Is generalize all of this because I want to be talking about toric origami manifolds and origami templates rather than this stuff. And so I think in the interest of time and trying to get, I think one of the things that Ana and I want to get out of you is, what are these combinatorial gadgets that we're looking at? What are the interesting combinatorial questions that we should be asking that we don't know to ask because we're not combinatorialists? So I'm going to skip some of the geometry, but I might tell you about the consequences. But I basically want to tell you what origami templates are sort of by the theorem. Well, actually, I was supposed to say something about 4 manifolds, too. So, well, maybe actually I should say that before I go on. So 4 manifolds are an interesting class. I mean, in 4 dimensions, I'm still trying to understand this better, but 4 dimensions is where the smooth Poincare conjecture, for example, is still open. And so there are, I mean, the topological questions and questions about exotic smooth structures are still not completely resolved and are interesting. The 4 manifolds that fit into the toric framework okay, so we could ask which 4 manifolds are toric symplectic. So they have a, oh, and I think this is what Ana and Doran were just talking about. And the answer, I'm supposed to say which simply connected. Well, no, maybe not. Let's just say which, well, toric symplectic manifolds are simply connected. So, okay, so we're not. So the toric symplectic ones include, we have S2 cross S2. And the only other ones are CP2 connect some K copies of CP2 bar. Okay, and so those all have, this we've already seen has polytope that looks like this. CP2 itself has polytope like that. When I take a connect sum with a CP2 bar, that's the same as chopping off a corner. Sorry? Oh, bar means I take the oh shoot, this, or did I write this down? I didn't write this down because it always confuses me. I take the opposite orientation. It turns out that that is not symplectic. Okay, that does not have a symplectic form. That does not have a 2 form whose top power is this opposite orientation. And it is also, I wrote something about it down somewhere, but I can't find it. Okay. So doing this connect sum with CP2 bar in the polytope world corresponds to chopping off a vertex. So I'm only slightly confused about something I wrote down, but oh, okay. So I'll get polytopes that look like that. And one should be careful because when I say which 4 manifolds are toric symplectic, this which 4 manifolds is maybe up to diffeomorphism, whereas the Danilov theorem was up to equivariant symplectomorphism. And I don't really want to get too mired in those details. But in any case, those are the simply connected 4 manifolds that happen to have effective 2 torus actions and compatible symplectic forms. Okay, so now what I want to do is sort of motivate toric origami manifolds by the theorem. I can erase this for right now. Log concavity is, I'll leave it there, but it's not going to be true. Let's see, so the theorem due to Ana da Silva, Victor Gilliman, and Ana. Oh, do you just write? Okay, is that compact toric. Toric still means the same thing. I have a torus of half the dimension acting on an even dimensional manifold. These are in one-to-one correspondence with origami templates. And what I didn't say about the Dalzant theorem, I'll just say the analogous thing here. So what was true for the Dalzant theorem was that this correspondence takes these up to equivariant diffeomorphism, preserving whatever your structure is. And over here, it's up to SLNZ plus moving around in the affine space. And so those, if you move your polytope around, you obviously still have the same manifold. If you SLNZ it, this business of you get it's a little work to show that it's equivariantly symplectomorphic, but it is. Okay, and so whatever these are, I can basically define them by what are called origami templates, and then I can do the same trick as before. I just take my template, cross with a torus. I think of my template essentially as the orbit space, cross with a torus, and collapse where I need to construct a manifold. Okay, so to understand the combinatorics, I'll just tell you what these origami templates are. And I'll erase it. Oh, right. I put up those 4-dimensional examples for a reason, which was this. So these are examples, whatever they are, they're examples of folded symplectic manifolds. Okay, so folded symplectic form is still a 2 form that's closed, but you relax the non-degeneracy in a very controlled way. And the point is, so understanding which manifolds are symplectic is a slightly subtle question, but understanding which manifolds are folded symplectic, it turns out, has a very nice topological interpretation. The folded symplectic manifolds, having a folded symplectic structure is equivalent to having a complex structure on not quite the tangent bundle, but the tangent bundle plus a trivial bundle. Okay, so, and this is something that, this is sort of a condition that comes up naturally in homotopy theory. The point is that every orientable 4 manifold has a stable, what's called a stable complex structure. And that means that every 4 manifold, every orientable 4 manifold is folded symplectic. And so every orientable 4 manifold is. In fact, every 2 manifold is. So orientable or not. Okay, so we now have a framework that includes all these 2 manifolds. Maybe not, well, okay, so the folded framework includes all of these and includes all orientable 4 manifolds. Okay, so that's sort of a motivation for why this is a reasonable class to study. Now the toric ones, I need to have an effective 2 torus action. And I'm going to sort of tell you, so part of the point is this degenerating in a very controlled way basically means that almost everywhere you have a toric symplectic manifold. And so everything that we proved, that I didn't prove already, but the sort of local condition about convexity and all of this, that is all still true. It's just when you hit these bad points that things go wrong. And they go wrong in a controlled way in the toric case. And so the idea is this. You sort of locally have these polytopes, these simple, smooth, rational polytopes. Okay, so locally I have this. Just along a facet, things might go badly wrong. So let's suppose that it went badly wrong along this facet. Well, what happens when it goes badly wrong along a facet is that I might hit this facet and then move into another polytope rather than staying in the same polytope. So there's a second polytope I might sort of mirror into. Okay. Okay, I can sort of pass. I mean, it's like one of these it's like one of these fancy fun houses where you're sort of coming along, you hit this, and then all of a sudden you pop out over here, and you come back in. And so the idea is that you have a bunch of Delzant polytopes, and they're glued together along facets in a controlled way. Okay, so an origami template is exactly that. We should think of them as actually glued to each other, yeah. Okay, and so the way I'll describe it is in terms of a graph. So I have a collection of polytopes, and then I have a collection of facets that are glued together along edges of the graph. Okay, so an origami template. Oh, first I have to say, let's see, D sub D is the set of all Delzant polytopes. I don't want to write out all those words. In RD, and E sub D is going to be the set, all subsets of RD that are a facet of a polytope in D sub D. Okay, so if I'm living in R3, I have these 2 polytopes are both elements of D sub D, and this square or rectangle is an element of E sub D. Okay, and then an origami template is a template graph G together with maps. Let's see, so for each vertex, I have a Delzant polytope, and for each edge, I have a facet, and these have to satisfy first of all, if my edge is joining vertices V and W, then the facet should be a facet in both the polytope for V and the polytope for W, and it should sit in them in the same way. So locally, there's like a little neighborhood of the facet that's isomorphic. All the edges, all the facets coming out are the same. Well, the facets don't have to be the same, but nearby, the beginning of them, they have to be the same. Exactly. I just sort of glue along the pink facet. I'm just sort of identifying the points in the pink facet. I'll write that down explicitly. But let me finish this first. So the other thing is I'm not allowed to, once I've glued that pink facet, I'm not allowed to glue any adjacent facet to it in either of the polytopes. You could have multiple edges, exactly. Just not nearby facets. So yeah, we could have, we have two identical ones. Exactly. Okay. Okay, so sorry, I'm just being a little sloppy, but you can't use any adjacent facets to any of the facets that you're using. Okay, so that's that. So multiple edges are allowed. Well, basically the idea is what I sort of want to do is what I did before, where I take my template, cross the torus, and I collapse along facets. And as that will produce you a manifold as long as the facets where you're sort of no longer collapsing are sort of far apart. If you tried to glue this and here, you'd have a problem with the manifold structure at that point. Nothing else makes problems. Yeah.
Wait, but could you? I mean, you could identify this facet with another polytope, with third polytope.
Yeah, yeah. So you could have something like this, and this, say, is glued to something like that, and this one I'm glued to something like so this saying that they have to agree means that I have to come out along the same directions, but and then I could have glued it to, say, a third one here. And I can even do horrible things like
But
I could do.
can't do the other three.
I can't use the other three now.
Anyway, with any
With anything else, that's right. That's right. I can also do things like, oh my gosh, I have to make sure I get this right. Okay, so now I could do. Ooh, I didn't do it right, did I? Oh no, I did do it right. I need another color. Okay, I could do something awful like that. And if I were careful, I would sort of, well, yeah, okay, that's fine. Okay, so I can do bad things, but, well, whatever that means.
And you cannot identify three in the same.
Yeah, you can only identify two at a single facet. That's right. And, oh, right, so the other thing I can do, so these always have edges that have two ends, like I've glued two things together. Okay, you don't actually have to glue two things together. You could just have one facet that's sort of by itself. Oh, so first, sorry, before I say that. Oh, I don't want to do that yet. I'll erase this. Okay, so what we want to do is then make something called the orbit space from this origami template, where I actually glue these things together. So maybe I'll call this O, the origami template. This is M mod T. This is the, first I take the disjoint union of all of these polytopes. And I'm putting an index vertex there just so that I'm abstractly thinking of these as not sitting in the same space. And then I glue together along, let's see, so let's see, V comma C, V comma Q is adjacent to W. Well, first I'm explaining what the orbit space should be. Yeah. So this is where I actually glue my. I mean, abstractly, I just have a bunch of polytopes with some facets, noted, and now I'm actually gluing them together. So here, okay, this, whenever there's an edge, VW, and P is equal to Q in P and Q are in that facet, and they're the same point in that facet. Okay, so I glue the same points to the same points. So that's just this business of. And now to reconstruct M, I just take this origami template cross T, and I divide out by another equivalence relation where basically this new thing, oh my gosh, I have to think about what the facets are. I forget about I don't use any of my pink facets that I glued together, but everything else is in a facet and is sort of in a facet in the Delzant way that it was before. So there I make the same equivalence relation as I had before.
You know the facets that you glue.
Exactly. So same equivalence relation as before, ignoring the glued facets. Okay, so a very simple example in one dimension is I might have, okay, so I'm going to always draw my template graph in brown because I don't want to use brown for anything else because I don't really like the color anyway. Okay, so my template graph is this. I have two vertices and one edge. Okay, so one way to, and my information is these are my two polytopes for each. Okay, so let's call this VW. This is the polytope for W. This is the polytope for V. And then the facet for that edge is going to be this. Okay, and so my orbit space, my origami template, I can think of as this. Okay, and so now I have this whole, oh my gosh, it's hard to draw. Well, okay, I'm going to draw it in two pieces. Okay, so I have I'm going to think of those pink things as glued together. And now I collapse along all the facets that aren't pink. So you sort of have that hemisphere glued to another hemisphere. Okay, and that's where the word folded comes from. I can really think of this as folded up. Okay.
So this the question in
Yeah.
general, you said that the theorem you said above
Uh-huh.
was you just restrict. It was the same as it was a restriction of the Peasant theorem.
No,
I mean, it's not restriction.
It's not a restriction. It's a different, yeah, I mean, it's sort of a bigger class of manifolds and a bigger class of combinatorial gadgets. Yeah, yeah. I mean, certainly it includes the Dalzant theorem where your template graph is a single vertex.
Right.
Yeah. Okay, so the other thing I can do, so here, oh, maybe I shouldn't get into this, but somehow, you know, I said that there were non-orientable examples, and RP2 fits really nicely in this whole framework. So, so if I have a sort of an edge with a single vertex, oh, then say this is my template. If I have a single vertex, I can think of this now as this, and in this dangling edge case, what I do is I identify antipodal points. And so what I get is RP2. Okay, and RP2 does have a circle acting with one fixed point, and so it's not unreasonable that you would want something like this to fit into the framework. The nice thing is that all of the examples here, wherever there's a circle action, they fit into the framework. So this has origami this has origami template, just it's a single vertex. Yeah, the Klein bottle also, and so the origami template in that case is it oh, but with no, it's a single vertex and two dangling edges. Okay, so it has two of these cross caps. It's just RP2 connect some RP2, the Klein bottle. The torus, you can do this as, oh, I guess, well, sorry, you can do this with template graph. I guess you don't need the extra one. Yeah, I guess you can just have template graph, sort of the top and the bottom. So, so you can have multiple edges. Okay, and then I just take the product of that circle with S. Well, okay, so I have an interval both times, and it's glued at the top and the bottom. And so I have a circle cross a circle, and there are no longer facets. So, so I get a 2 torus. Okay. Oh, let's see. So what I then want to say is something like this. Like you can still somehow see the topology in terms of the combinatorics of this thing. Oh, did I skip something? I said all of that. I said all of that. I'm not going to say that for right now. Maybe I'll say it later. Yeah, okay, so I guess I just should say some things about the topology of this. They do. They do, and I'll talk about those in a special case. I haven't figured out how to use them in every case. But the first thing you need to think about is whether the manifold is simply connected. And in the simply connected case, you still have this very nice H vector, F vector correspondence. Okay, but the first thing you show so we were sort of, so I proved this with Ana, but we were building on some earlier work of Masuda and Park. So pi1 of this manifold is isomorphic to, well, first of all, we're taking the origami template across the torus modulo something, and so you sort of expect any cycles in the origami template to still be to still contribute to the fundamental group. So that's true. The fundamental group of M is isomorphic to the fundamental group of the orbit space. Cross, you have to add a little finite, well, it's maybe not finite. What this is a lattice correction. So let me say, first of all, what each of these factors is, and then I'll give you examples for how they show up. So this, that's the fundamental group of that origami template. It turns out the origami template, everything deformation retracts to the template graph. So this is really just the fundamental group of the template graph. So it's a free group. Okay, let's say it has rank K free group. And then the correction that I added, this is just a lattice correction, and what it is you take, N we think of as the full lattice, ZD, and N sub the orbit space is the span of these new Fs, those normal vectors to the facets, for every facet that I haven't glued. Okay, so I take the Z span of all of those things. Most of the time, that's the whole lattice. But the point is, like in these examples, if I had a fixed point, then all of the edges coming out of that fixed point Z span, that's equivalent to saying all of the normals to the facets that meet at that vertex Z span. And so if there's a fixed point, that lattice correction goes away. So it's only when I've sort of glued all of the fixed points that I could potentially have an extra correction. And because of this business because I always have D minus one facets still around for any edge in the origami template, this is at worst a co-rank 1 sublattice. So this correction is either going to be a trivial group, a finite cyclic group, or a copy of Z. And all three of those can show up in this simple example, it turns out. Okay, so if I take template graph, that, and if my two pieces are, let's see, I can do rectangles, I can do something with slope -1, I can do something with slope -L. Those are all Delta polytopes. And then if I take two copies of each of those and glue along the top facets and along the bottom facets, well, I can just look at the lattice corrections. So here I have my normals are the same, and so they only span a Z. So my lattice correction is going to be Z. Here, let's see, I have -1, 0, and 1, 1. Those Z span, so I get a trivial lattice correction. And here, I have something like that, and so I get a Z mod LZ. You can actually explicitly identify the manifolds in this case. So in each of these cases, M, let's see, so here M is going to be S2 cross S1 cross S1. Here we're going to have S3 cross S1. And here we're going to have a lens space cross S1. So a lens space is just a sphere divided out by a Z mod L action, a free Z mod L action. And so this has fundamental group. Well, there's the Z mod LZ for this and the Z for this. Here we have a Z for each factor. Here we just have a Z for the S1 factor. And here we have a Z mod LZ and a Z. Okay, so all three of those can occur. Okay, but this is sort of, I mean, these are sort of the exceptions. And sort of nicer things happen when you're simply connected. Okay, so well, so actually what is true is that O is simply connected if and only if M is simply connected. So you can only, I mean, so if M is simply connected, well, both of these have to go away. In particular, this has to go away. But if this is simply connected, well, it turns out then you have to have a fixed point, and so you can't have this lattice correction. So this is an if and only if. And what happens in this case is that you do get, again, this F vector, H vector business. Okay, and so what I mean, you have to be careful how you count. We no longer count anything that's on one of the glued facets. But for example, actually, I'm going to do. Yeah, so what I should say is the F vector here is counting the number of K facets, K faces of O. And here, you do the same translation, but what this ends up counting is the Betti numbers of M. Okay, and so this fact is due to Masuda and Panoff. Yeah, Masuda and Panoff implies this. Okay, and so this business of counting carefully, I'll show you a quick example. So we can do S6 in the same way as we had S4, and I'm doing S6 just because it's a slightly bigger polytope. Okay, in both cases, what happens is that the template graph is this. Each vertex has the same polytope, a simplex, and the facets that I glue, I take 2 copies of that and I glue them along this. Okay, so that's my O sort of superimposed. Okay, and then the point is, when I want to count, it's easy to count vertices. I just don't count things on the pink. So there are 2 vertices. There are 3 edges, because there are edges that start at this vertex and go up. I can go back into the board. Oh, no, I'm not supposed to use pink. I can go back into the board. Or I can go along. So there are 3 edges. And then there are, for the facets, there's the facet in the xy plane, in the in the xz plane, in the yz plane, and the xy plane. Okay, so there are 3 facets. And then, does everybody know how there's this F vector, H vector Pascal triangle trick? So you put the F vector along, you start with a 1 for one polytope. And then, I better get the right order. And then I do facets, so 3, 3, 2 in a triangle. And now I put 1s all the way down. And I fill this in. So whatever number I fill in here, the rule is that this plus this has to equal that. So I fill in a 2 there. And then this plus this has to be 2, so that's 1. 2 plus this has to be 3. Did I do this right? 1 plus something has to be 1, so that's 0. 1 plus something has to be 1, so that's 0. 1 plus something has to be 2, so that's 1. And now I see this is my H vector. This is exactly the Betti numbers of S6. This is beta 0, beta 2, beta 4, beta 6. Okay, and so that works as long as you count in this funny folded way. The facets fold. So it is known that this is true, but I think that's as far, I don't know that people have understood very well what the combinatorics is here that one would want to use that for, or what the, where's the example that I want to use? I mean, the problem is, well, we have a lot of cases where this isn't a simplicial complex anymore. I mean, this has no vertices and it has 2 edges. So what the thing is, I don't quite understand. The other thing that I want to say that generalizes, okay, so this is sort of to compute H star of M when M is simply connected. When M is simply connected, we can do the same thing to compute HT star. And again, there are sort of 2 points of view. There's the face ring and there's the piecewise polynomials. Both of these interpretations work. So we have the face ring. This is due to Masuda-Panov. And we also have piecewise polynomials. This is what Ana and I worked on. And what the piecewise polynomials is on is some combinatorial gadget called a multifan. So what I have to do is take maybe I just want to explain to you what the multifan is here. So for each facet, again, I take a ray, and I glue cones along things where things have to intersect. And the problem is that you just don't get what you would have expected to get. So for example, I'll draw a 2-dimensional one because I can't do the 3-dimensional ones very easily. So for S4, the same thing would have happened. We have our and so my multifan is going to consist of, let's see, so I have a ray like this. I have a ray like this, a ray like this, and then I fill one cone in between those 2 rays for the white vertex, and one cone in between the 2 rays for the purple vertex. So it's this double. There are 2 cones there filling in the same, adjacent to the same set of rays. Okay, and so then this piecewise polynomials, you put a polynomial on each maximal cone, and the condition is that they have to restrict to the intersecting cones and agree on those restrictions. Okay, so that's that. In this F vector, H vector doesn't work when you're not simply connected, but you can still say some things. So what you can say okay, so when we're not simply connected, what I will say is that when this correction is z, it turns out you have to be in a very special case. What happened here when this was z was that we got S2, which remember is symplectic, cross a 2 torus. And that actually has to happen in general. M has to be isomorphic to something symplectic cross a 2 torus. And so that's very special. And also, in particular, you can compute everything you wanted to know. You know already because of Kuhne's theorem. Okay, and then in the other cases, well, Ana and I have been working on this. Sometimes you can say things and sometimes you can't. In 4 dimensions, we can compute all the Betti numbers, and they're sort of related to the fixed points in a way that you would expect. Okay, so we have Poincare duality, and we're only in 4 dimensions. So I just have to tell you when I is 0 and 4, well, of course, we always get a single. We just have z or r. When I is 2, and when I is 1 or 3. And Betti numbers are just ranks. So we know from the fundamental group that, well, this was just a free group of rank k. So this is going to be k. And the only thing remaining is that. And if you just sort of play with Meyer-Vietoris, what you get is that this is the number of fixed points minus 2k. Is that right? I think it's 2k plus 2 minus 2. Okay, so that's the formula that you get. What you deduce from this is that the Euler characteristic is always equal to the number of fixed points. Okay, if you just add up minus plus minus plus. Okay, yeah, so there's some relationship between, there's something going on, but I don't understand it. The odd Betti numbers are not 0. Yeah. There are some cases, right, so I should mention there's some work of some guys whose names I remember. There's work of Eisenberg, Masuda, Park, and Zhang. Okay, they work in a case, they make an assumption on the origami template that I have no idea if it's a reasonable assumption or not. They assume that every face, except for the whole thing might have cycles, but they assume that every face is acyclic. So if every proper face. And what they get in that case is that the only odd Betti numbers that are 0 are h1 and h2n minus 1. And in that case, they also managed to do some of this. So when the thing is simply connected, I don't know, there's some subtle relationship between f vectors, h vectors, and equivariant cohomology. And under that assumption that I don't really understand the combinatorics of, they managed to recover most of the equivariant cohomology because stuff that goes wrong is only really in degree 1. So I guess that's where we are. Did we have other? I mean, so I guess our questions are, what combinatorics should we be looking for in O? Is this kind of assumption something you've seen before? Proper faces are acyclic. Oh, it means that the homology is 0, the reduced homology. So in particular, they're connected. So for example, something that could go wrong. Oh, right. The ones I just erased are all wrong because the faces are the edges are these circles. So that's bad. But ooh, something like this one is actually okay, except that one's non-orientable. So never mind. Okay, they give some examples. So there are examples, but I haven't been able to really understand what it is that makes all the examples, what they all have in common exactly. So you can do something like, do something like that. And well, okay, so now my edges are, let's see, I have the ones that just go straight across. That's a terrible color. The ones that just go straight across, and then the ones that get folded, but they're still acyclic. Yeah, the edges aren't circles, so it's sort of okay. I mean, I guess somehow the idea is that you haven't, I don't quite know. Maybe one could play with it. I should say, the other thing I should say, the reason Masuda-Panoff applies here, like there's a whole number of generalizations of toric manifold. And most of them have to do with take a combinatorial gadget, cross it with a torus, and collapse along some of the subsets of the combinatorial gadget. For toric origami manifolds, we've sort of seen how to do that. A condition that naturally comes up is that the manifold itself has to be locally standard. So the torus action locally has to look like Tn acting on Cn. Around the action around the orbits has to look like that. And you can, so this example fits the origami structure, but it doesn't fit that locally standard because the orbit that I've drawn in green, if you look around it, it's exactly this. Well, if you cut that circle out, it's a Mobius strip, and so you have this thing going around twice, and that's not that doesn't happen in Cn or C. So that's all I have to say.